Welcome. The topic of this video is the amalgamation technique, à la Friezas. Our goal will be to construct countably infinite structures with a large automorphism group. The starting point are certain classes of finite structures. And the key property here is the so-called amalgamation property, which can be combinatorially quite tricky to check. So the entire subject is between permutation groups, infinite permutation groups, finite combinatorics, and model theory. We will restrict our focus to relational signatures because it's somewhat simpler, and the whole theory can be easily generalized to structures that also involve functions. To recap some terminology, if we have two structures A and B with the same signature, then I write A hook arrow B if A embeds into B. In other words, A is isomorphic to a substructure of B. The age of a relational structure B is the class of all finite structures that embed into B. This is not exactly the same as the set of all substructures of B, because the age is automatically closed under isomorphism. And this is also why we have to say that the age is a class and not a set. I will start with some easy observations about ages. First of all, the age of any structure has the JEP, the joint embedding property. A class has the JEP if for any two structures A1 and A2 in the class there exists another structure C in the class such that both A1 and A2 embed into C. Of course, the image of A1 and A2 under these embeddings might overlap, but still it is obvious that the age of B has the JEP, because we can simply take the substructure of B whose domain is the union of the images of the two embeddings into B. And this substructure of B embeds both A1 and A2. Second observation. Clearly the age of any structure is not only closed under isomorphism, but also under substructures. This is clear because if A embeds into B, then any substructure of A also embeds into B. You just have to restrict the embedding to the substructure. The property to be closed under substructures is sometimes called the hereditary property, HP. Our first lemma shows that these conditions of classes of finite relational structures characterize the property of being an age. To formulate the lemma, we fix a relational signature tau. Let C be a class of finite tau structures. Then C has the joint embedding property, is closed under substructures and isomorphisms, and is countable up to isomorphism if and only if it is the age of a countable tau structure B. We have already proved the backwards direction. For the proof of the forwards direction, we fix an enumeration C0, C1, C2, and so on of representatives for all isomorphism classes in C. Such an enumeration exists by assumption. The structure B we are looking for can then be constructed as a countable union of a chain of finite structures AI, where AI is defined inductively as follows. We start with A0, which we set to be C0. For the inductive step, suppose that we have already constructed AI. Then by the joint embedding property, we find a structure D in our class C, such that AI embeds into D and Ci plus 1 embeds into D. Then AI plus 1 is said to be an extension of AI, which is isomorphic to D. So AI is a substructure of AI plus 1, and AI plus 1 embeds C0, C1, and so on until Ci plus 1. So the limit embeds every structure of our class. Using the hereditary property, it is not difficult to show that this structure does not embed structures that are not in C. And this is the proof. Let's have a look at some examples. We start with a non-example to motivate the assumption of the lemma that the class C is countable up to isomorphism. Let tau be the signature that contains infinitely many relation symbols, R1, R2, and so on. Say all of arity 1. and let C be the class of all tau structures. Then there are 2 to the omega many non-isomorphic one-element structures in C. Because for every relation we can decide whether or not the only element is in the relation or not. But a countable structure can only have a countable number of finite substructures. So the assumption is necessary. In our next example, the signature consists of a single binary relation symbol, and C is the class of all tau structures where the relation symbol denotes a strict linear order. Note that the class C is countable up to isomorphism. Every class of finite structures with a finite signature has only countably many isomorphism classes. Here, it is even true that for every natural number I, there's only one linear order with I elements up to isomorphism, which we denote by Ti. It's clear that C is closed under isomorphism, substructures. It's also clear that the class C has the JEP, because if you have 2 linear orders A and B, then A embeds into B, or B embeds into A. So A embeds both A and B, or B embeds both A and B, and that proves the JEP. So the lemma says that there exists a countable structure whose age is C. And indeed, the strict order on the integers would be such an example. But we also see that the countable structure is far from being unique. Another structure whose age equals C is the strict order of the natural numbers. I would also like to mention that the automorphism group of the strict order is not large. There are only countably many automorphisms, the shifts. And the automorphism group of the strict order of the natural numbers is even trivial. The only automorphism is the identity. We will introduce next a quite remarkable property of relational structures that implies that the automorphism group is large. Moreover, the property implies that there is only one structure of a given age with that property. And this property is called homogeneity. A relational structure is called homogeneous if every isomorphism between finite substructures can be extended to an automorphism. Here in my picture, the structure is called B, and the isomorphism is called F. Homogeneity can equivalently be phrased as follows. If 2 tuples of elements of B locally look the same, that is, if they satisfy the same atomic formulas, then the 2 tuples also globally look the same. That is, there is an automorphism of the structure B that maps one tuple to the other. Let's again start with a non-example. The linear order of the integers is not homogeneous. For example, the substructure with the 2 elements 0 and 2 is isomorphic to the substructure with the 2 elements 0 and 1. But this map that maps 0 to 0 and 2 to 1, this map cannot be extended to an automorphism of the entire structure because we do not know where to map the element 1. In such arguments, it is convenient to draw the structure twice, so that the map F and its extension can be drawn from left to right. An example of a structure which is homogeneous is the strict linear order of the rational numbers, Q. To prove the homogeneity of this structure, we use a very important proof technique in model theory, namely the so-called back and forth argument. To prove the homogeneity of Q, we first fix an enumeration, Q1, Q2, and so on, of all rational numbers. Suppose we are given an isomorphism F between finite substructures of Q. We have to find an extension of F, which is an automorphism of Q. We do this step by step, by finding an extension G of F by one more point. And we repeat, and eventually we have defined a map which is defined on all of Q. To define this extension G, we pick the smallest index I, such that F is not defined for Qi. We claim that there is a rational number R, such that the extension of F that maps Qi to R is an isomorphism between finite substructures of Q. Well, and here we simply use the fact that Q is unbounded and dense. So we will always be able to find such a point R, no matter how F looks like. If you would continue forever like this, extending F and extending the extension and so on, we would obtain a function which is defined on all of Q and an embedding. However, we cannot guarantee that the resulting map is surjective. We have to make sure that eventually every element of Q is hit by the map that we want to define. The extension above is called going forth. What we have to do now is, to fix the surjectivity issue, is going back. This time we pick the smallest index j, such that qj is not in the image of f. We want to find an extension g of f such that qj is in the image of g. So we need to find a point s such that the extension of f that maps s to qj is an isomorphism. But such a point S can again be found easily by the assumption that Q is a dense and unbounded linear order. We then iterate these steps, alternating between going forth and going back, going forth and going back forever. In this way, we make sure that eventually every point is in the domain of the map and that eventually every point is in the image of the map. The resulting map preserves the order, is bijective, and hence an automorphism of Q. If a structure is homogeneous, then this has a remarkable consequence for the age. A class C has the amalgamation property, abbreviated by AP, if for all structures A, B1, and B2, such that A embeds into both B1 and B2, there exists a structure C in the class and embeddings of B1 and B2 into C, such that the composition of the embedding that goes from A to B1 with the embedding that goes from B1 to C equals the composition of the embedding that first goes from A to B2 and then from B2 to C. Note that if we allow structures with an empty domain, then the AP implies the JEP. Otherwise, they are incomparable. So the following diagram commutes. It's quite easy to see that the age of a homogeneous structure has the amalgamation property. I will give a short proof by drawing a diagram. If we have A, B1, B2, then they are isomorphic to substructures of B, so I will draw them as substructures of B. So I have a structure A, which embeds into both B1 and B2. We can then go from the copy of A in B1 back to A, and from there we can go to the copy of A in B2 and obtain an isomorphism between finite substructures of B. By the homogeneity of B, this isomorphism can be extended to an automorphism of B. To find the substructure C of B that we are looking for, we apply the automorphism that we obtained to B1. I claim that the union of the image of the automorphism of B1 with the domain of B2 is the desired amalgam. And indeed, this is witnessed by the restriction of the automorphism of B to B1 and the identity on B2. Now it's natural to ask for a converse. Suppose that we have a class C of finite structures which is closed under isomorphism substructures and has the amalgamation property. Can we then find a homogeneous structure B whose age is C? The answer is provided by Friezas' theorem. Again, we will be interested in the situation that we can choose B to be a countable structure. So a class of finite relational structures with the same relational signature is called an amalgamation class if it is not only closed under isomorphism in substructures and has the amalgamation property, but also if it has countably many isomorphism classes. Friezas' theorem states that for every amalgamation class, there exists a countable homogeneous structure C whose age is the given class. Moreover, C is unique up to isomorphism. This structure C is called the Friezas limit of the class, sometimes denoted by flim. The uniqueness part can be proved by a back and forth argument, just as we have seen it for Q. Instead of using the density and unboundedness of the order of the rational numbers, we now use homogeneity. We therefore only have to prove the first part of the theorem, the existence of the Friezas limit. We can construct the Friezas limit as follows. First, I need to introduce the following variant of homogeneity, often called weak homogeneity. A structure C is said to be weakly homogeneous if for every structure B in the H of C and every substructure A of B, every embedding F of A into C can be extended to an embedding of B into C. I will draw the situation here on the right in a diagram. It is relatively easy to see that homogeneity implies weak homogeneity. So I suggest you to press pause in the video and do this as an exercise. This is not difficult. Quite surprisingly, the converse is true as well. To see this, observe that in the back and forth argument, to prove the uniqueness of a homogeneous structure with a given H, we in fact only needed weak homogeneity, not full homogeneity. The Friezas limit is defined using a countable chain of structures Ci in our class, such that if B is in the class and A is a substructure of B, then every embedding of A into some Ci in the chain can be extended to an embedding of B into some Cj in the chain. In this way, we make sure that the limit of the chain is weakly homogeneous. Also note that the H of the limit of such a chain is precisely the class we started with. This is again not very difficult, and I suggest to do this as an exercise now. So all we are left to prove Friezas' theorem is to construct such a chain. The idea of this proof is very natural and appears in many other proofs in model theory. The definition of the chain is by induction. C0 can be set to an arbitrary element of the class C. Suppose now that Ck is already constructed, so Ck is a finite structure. In order to satisfy the required condition for our chain, we have a lot of tasks to do. Each task can be seen as a triple A, B, F, where B is a structure in the class, A is a substructure of B, and F is an embedding of A into Ck. The task is to make sure that our chain contains a Zj such that F can be extended to an embedding of B into Cj. Of course, I can define Ck plus 1 to take care of this task simply by the amalgamation property. I amalgamate Ck with B over A. But in this way, I create lots of new tasks for Ck plus 1. And I have just satisfied one task for Ck. But there are infinitely many tasks left for Ck. So here comes the trick. We make a big list of all the tasks. Luckily, there are only countably many. So let A sub ki, B sub ki, and F sub ki, for I in omega, be an enumeration of all the tasks for Ck. I have to make sure that these tasks are dealt with for every I in omega, but also for every k in omega. So I fix a bijection alpha between omega squared and omega. Let ij be such that k equals alpha of ij. Then Ck plus 1, the structure we have to define in our inductive step, is defined as the amalgam of Ck and Bij, so that Fij extends to an embedding of Bij to Ck plus 1. In this way, I make sure that every task is eventually dealt with. and hence our chain has the desired property. I will discuss next a series of important examples of amalgamation classes and their Friezas limits. Our first example is the class of all finite undirected graphs. This class is clearly closed under isomorphism, and it is also closed under substructures, because substructures of graphs are again graphs. Usually, the amalgamation property is the interesting property to check. When checking the amalgamation property, we are given a structure A in the class and embeddings of A into other structures B1 and B2 in the class, and we have to find an amalgam in the class. We may assume that A is in fact even a substructure of B1 and a substructure of B2, and that E1 and E2 are the identity map, because the class C is closed under isomorphism. So we may rename the elements of A and of B1 and B2 along the embeddings E1 and E2, so that A is indeed a substructure of B1 and B2. We may also ensure that the intersection of B1 and B2 is precisely A. This has the advantage that we may draw the entire situation in one picture, which we can then use to find the amalgam. This observation not only holds for graphs, but for all isomorphism closed classes. In the case of graphs, finding the amalgam is really easy. Let C be the graph whose vertex set is the union of B1 and B2, and whose edge set is the union of the edge sets of B1 and of B2. The resulting structure is sometimes called the free amalgam of B1 and B2. In general, the free amalgam might not be in our class, but in our case, where C is the class of all finite undirected graphs, the free amalgam is again a finite undirected graph, so it is in C. And indeed, the free amalgam satisfies the requirements of the amalgamation property, because both B1 and B2 embed into C via the identity map, and of course, identity maps commute with respect to composition. Even though the amalgamation property is in this case trivial to check, Friezas' theorem produces a very interesting limit object for this amalgamation class. It is a countable, homogeneous, undirected graph, which embeds all finite graphs, and it is unique up to isomorphism with these properties. So this graph is sometimes called the random graph, for reasons that I won't explain in this video, but sometimes it's also called the Rado graph, after one of the mathematicians who discovered it. Our next example is the class of all finite tournaments. A tournament is a directed graph with the special property that there are no self-loops, and between any two distinct vertices there is precisely one directed edge. So there are no double edges and no incomparable vertices, but there might be directed cycles in the graph. The motivation for the name tournament is that we imagine the vertices as, say, football teams, where each team played against every other team, and we had precisely one winner in each of the matches. And this winner, who is the winner, is represented by a directed edge. Again, closure under isomorphism and substructures is immediate from the definition. For the amalgamation property, note that the free amalgam is no longer a structure in the class. In the free amalgam, there are still no loops and no double edges, but there will be pairs of vertices that are not linked by an edge, which is not allowed in tournaments. But this is easy to fix. We define our amalgam structure C to be the free amalgam, where we add some additional directed edges until the structure is again a tournament. Since we only add edges between the complement of A in B1 and the complement of A in B2, this does not affect the property that the identity map is an embedding of B1 into C and of B2 into C. So we really found an amalgam. The Friezas limit of this class is called the countable universal homogeneous tournament. Again, a very beautiful infinite structure that we will study later. Example 3 is the class of all finite posets. Poset is short for partially ordered set. So we have a transitive, reflexive, and antisymmetric relation. I have drawn an example of a poset on the right. This class is again closed under isomorphisms and substructures. For the amalgamation property, the free amalgam is in general not in the class. I have drawn you an example where this happens. But this time we can't just fix it by adding some edges. In fact, we have to add certain specific edges to the free amalgam, namely the edges from the transitive closure of the free amalgam. I claim that the resulting structure provides an amalgam of B1 and B2 over A. All edges in the transitive closure of the free amalgam are between the complement of A in B1 and the complement of A in B2, so the identity maps are still embeddings of B1 and B2 into C, and C is in the class. It's a poset, and this is all we need. The Friezas limit of this class is sometimes called the countable universal homogeneous poset. Our final example for today is the class of all finite strict linear orders. The strict is actually not so important in what follows, but it has the advantage that I don't have to draw the self-loops in my illustrations. Again, closure under isomorphism and substructures is trivial to check. For the amalgamation property, again we can't use the free amalgam. This time even the transitive closure might not be in the class, because it might contain still incomparable elements, which is forbidden in linear orders. In my picture, I don't draw edges that lie in the transitive closure of the edges that I draw, to avoid clutter. To find amalgams in this class, we combine the amalgamation idea for posets with the amalgamation idea for tournaments. We first compute the transitive closure. If the resulting structure contains incomparable elements, we add one edge between the incomparable elements and then compute the transitive closure again. If the resulting structure still contains incomparable elements, we continue in this way until we eventually arrive at a linear order. And this linear order provides the amalgam. The Friezas limit of this class is a homogeneous linear order. And since there is only one homogeneous linear order by Friezas' theorem, and since Q is homogeneous and a linear order, the Friezas limit must be equal to Q. We close the video with an exercise. Which of the following three classes are amalgamation classes? 1. The class of all finite trees. A tree is a connected, undirected graph without cycles. 2. The class of all finite forests. A forest is an undirected graph without cycles. Equivalently, it is a disjoint union of trees. 3. The class of all triangle-free graphs. A graph is triangle-free if it does not embed the K3, the clique with 3 vertices. So in other words, there should not be 3 vertices in the graph so that all the 3 vertices are pairwise connected by an edge. The topic of the next video will be types. Types are a central concept in model theory, to analyze structures, to analyze first-order theories, and homogeneous structures are particularly well behaved with respect to types. So the Friezas limits that we have seen today will show up many times again later in the course.